Alright, so let's take another look at solving for bending deflections and beams. I went ahead and loaded the program up here on this floppy disk, and so I'm going to get it started up for us. It seems like my computer doesn't have a floppy disk drive. But as you can see, if you've never seen a true floppy disk, it actually flops. And I was thinking, what happens if we take a look at a problem where we hold one side and fix it, and we put our force out here on the end? We're going to imagine the beam will do some sort of bending like that, right? This is our classic cantilever beam with a point load on the end. So we're not going to look at it for a floppy disk, we'll look at it for an actual beam, but go ahead and check out this example. Gnarly dudes and dudettes. All our example problems are getting the spirit of 90s day, so our load P is 9.090 kips applied to the end of this cantilever. So let's set up our X and Y axis and sketch the deflected shape if we can. I think we can kind of visualize this deflected shape. We just saw it on that floppy disk. It just kind of flops over, bends downward, so it's kind of concave down. All right, so like all the other problems, we need to get started with drawing our shear moment diagram. So I'm going to leave that up to you. Go ahead and pause the video right here and draw those shear moment diagrams for me. And hopefully this is what you got for your shear moment diagrams. So if you're having trouble with this, go back to some of the stuff you learned back in statics or what we learned earlier this semester, what we reviewed earlier. Now I want to talk about the boundary conditions. So again, try to visualize what the boundary conditions are. I usually like to start with deflection. Where do we know deflection? Well, we know that the deflection at the fixed end has to be 0. So our first boundary condition, y of 0 equals 0, deflection at A equals 0. What else do we know about fixed ends? Fixed ends have a slope equal to 0. So this is a big boundary condition. Anytime you see a fixed end, go ahead and put this boundary condition in there. The slope at A equals 0 because it is fixed at point A. Now the moment 0, well, the moment 0 has a value. From our moment diagram, we see that it's negative PL. Or if you don't like to use a value, you could use m of L equals 0. Both of these would work. These will help us solve for our constants of integration. We can also get some values off our shear diagram. The shear diagram is P at all locations. So V of 0 equals P, V of L equals P, V of L over 2 equals P. Everywhere it is just the force P. Now, we're going to do our method of integration to solve this problem. But we know that from the fourth order differential where we come up with that, we say y to the fourth is equal to negative omega. Now, do we have a distributed load on this beam? No. Hopefully that was the answer you guys came to. So we would just write y to the fourth equals, well, basically equals 0. So if you're comfortable using this to start the solution to your problem, go ahead. We'll be able to integrate back from here. I do have to mention that we need to integrate on spots where the moment diagram remains continuous between one point to the other. So if your moment diagram makes a sudden change when you're using method of integration, you'll have to take that into account. All right, so in method of integration, we had all of these relationships. Now we can start at any of these relationships to start to solve our problem. The last, in example 1, we used the fourth order differential equation relationship. But we can just as well start from the moment relationship, EIY double prime equals m of x. Perhaps that's going to be the easiest for this problem that we have in place. If you're comfortable writing equations, algebraic equations for linear lines, coming up with the value for the moment diagram should not be too hard. So, and I added an EI in there. I forgot to put that in there the first time. So if you're not comfortable coming up with the equation for the moment, you could just come up with the equation for the shear. The equation for the shear is very straightforward. It's just the load P. So we can start from the shear and get back to the equation for the deflection perfectly fine. Now, if we want to come up with the equation for the moment, we can, right? It's just a linear line. Equation of a linear line equals mx plus b. Our y-intercept is negative PL, and the slope of the moment is the shear, so the slope is P times x. So this gives us negative PL plus PX. We can even try it out. If we plug in x equals 0, we get negative PL. When we plug in x equals L, we get 0. So we see that that's the equation for the moment. All right, so we can start from the top there and we can integrate. If we were to do that, the integral of 0 is a constant, so it's not 0. So make sure we remember that from calculus. The integral of 0 is a constant. That constant would be C1. We would then set C1 equal to V of 0, which equals P. So then we would find C1 equals P. All right, if we started from the shear, if you just jumped in there and you integrated, you would get that the moment would have to be px plus c2. So we'll jot that in place. Right, and then we also came up with the boundary condition that m of 0 has to equal negative PL. So that would then indicate that C2 has to be negative PL. So this now gives us EI y double prime equals negative PL plus PX. Okay, and this is what we, just using algebra, what we came up with from the moment diagram. So if you're more comfortable integrating, go ahead and do that. If you'd rather just jump in right from the moment diagram, you'll be perfectly fine and maybe get to the solution a little bit faster. Integrating both sides of this equation gives us EIY prime equals negative PLX plus PX squared over 2 plus our third constant of integration, C3. We had the slope condition. We knew that y prime of 0 equals 0 because the slope at the fixed end has to be 0. So plugging in y prime of 0, everywhere we see x, we plug in a 0. And so this will then lead us to the result that C3 in this instance has to be equal to 0 to make this algebra work out. Finally, we can integrate one more time from our slope to get to our equation of our deflected shape. So I'll just rewrite that without the constant C3, integrate both sides, and now we have the result EIY equals negative PLX squared over 2 plus PX cubed over 6 plus C4. Lastly, we use our last boundary condition, y of 0 equals 0. So plugging that in, making sure I swing my EI to the other side. I see that all the terms with x are going to become 0. So then I'm just left with C4. C4 has to be 0 in order to make this work. Rewriting our equation, y of x equals 1 over EI times the quantity of px cubed over 6 minus plx squared over 2. And that is our answer for our deflected shape. So if we want to come up with the deflection at any point along this cantilever, all we have to do is plug in a value of x, and we would be able to solve for that deflection. Now, this particular problem asked us to solve for the deflection at the tip of the cantilever, so at the far right end. So that is at a value of x equal to L. So if I plug in y of L into this equation, I now have y of L equals 1 over EI times the quantity of PL cubed over 6 minus PL times L squared over 2. So that becomes PL cubed over EI times 1/6 minus 1/2. So I can do a little bit of math, and that's going to give me a negative PL cubed over 3EI. Again, the negative sign is just from XY coordinate system. Because the deflection, y, is going to be lower than the x-axis. That's what the negative means. It just means that the deflection is downward. All right, if we go ahead and we substitute y of L being 120 inches, again, make sure you keep all the variables in this in the same units. I'm going to use all kips and inches. So plugging in a value of L equal to 120 inches, and our value for P, our value for E, and our value for I. We can solve for the deflection at the tip of this cantilever. In the spirit of 90s day, it should be no surprise that the deflection here is negative 0.9090 inches at the end of the cantilever. It's almost like I planned this whole lesson out. I don't know. Go figure. Anyhow, I hope you're enjoying the lesson so far. Hopefully you're grabbing these examples. In example 3, we're going to have you give it a shot, and I'll be there to help you out.